Throughout our work on differentiation, further differentiation and applications of it, we've looked at how we can use it to calculate several different things. These include stationary points of graphs, maximum and minimum values within a set interval or a closed interval of something, gradients and rates of change. What we're going to look at is taking this and doing one of the most important types of application with it, which is optimization. We're going to look at how we can optimize something to get us the maximum or minimum of whatever the scenario is that we're looking for. Now, when we're looking at this, there's a couple of key things to remember. The first thing is that when we're asked to calculate the maximum or minimum values for a function, there's certain phrases or words that can be used. So things like find the smallest, find the greatest, find the biggest, find the lowest, asking you to find an extrema somehow. So a maximum or a minimum of a scenario. These are the kind of things that as soon as you see them, instantly you should think, right, I'm going to have to do a bit of optimization here. Let's think at how we differentiate and what that actually means. Now, when we are optimizing something, there's a few key steps you should follow to help you get to where you need to get to. What we need to do is think logically. Now, when we're at a maximum or a minimum value, our overall value is not changing. We're at the highest or the lowest point of something that we possibly can get to. If you think of it in terms of a graph and a stationary point, it is that point where it's a stationary point. The graph has stopped changing for that microsecond, so we're at a peak. What this means is our derivative is equal to 0. So we can take this fact and use it to solve problems that looked at optimizing a scenario. So we could solve them by setting the derivative equal to 0, solving the equation, and then looking at the nature of these points. Now, if it's a maximum, the nature will tell us it's a maximum turning point. If it's a minimum, the nature will tell us it's a minimum. But we can't just assume that the answer we've got is one of these answers. We have to show it is. We have to be able to say, right, I've got this value. This is a maximum or a minimum because my nature table shows it is one of those points. Now, the best way to have a crack at this is for me to show you exactly what I mean, and then you can have a crack at the questions in the other video. So, imagine I'm given this scenario. So there's a cuboid with an open top. It has a base which is x centimeters by 2x, and it's h centimeters deep. It has an outer surface area of 24 centimeters. So first thing I want to do is show the volume is given by this. So v of x equals 2/3 x bracket 12 minus x squared. And b, find the value for which x gives the maximum volume, and then what is that volume? So calculate the answer at the end of it. This is the kind of question we have to answer. So the first thing I have to do is look at part A. So look at this bit here. So I want to show the volume is given by this. Now it's a cuboid, so we know that the volume of a cuboid is length times breadth times height. Now our length is given by the x, our breadth is given by the 2x, and our height is given by the h. So what I can then say is length times breadth gives me 2x squared, and then it's times h. So I've got 2x squared h for my volume. Now, we want to get to this. Now, the way we do that is we have to find some way of getting rid of the h. It doesn't exist in our final equation, so we want rid of it. But what can I use to get rid of it? Well, that's where the second bit of information comes into play. The outer surface area is 24 centimeters. Now, think of what your cuboid looks like. Cuboid in this case, it didn't have a top, so we can't worry about the area of that. But it has 4 sides and it has a base. Now the base, the area of the base is given by x times 2x. So that tells me that my base is 2x squared in size. Now for the sides, I've got the side here and the side at the back. They're the same. And my two sides, either side of it, are also the same. So what I can do is calculate the area of the front, the area of the right hand side, and then double it. And if I add all these values together, I get what my surface area is going to be. So if I take this one here, I've got my base along the bottom times my height. So in this case, I'm going to have 2x times h, so I get 2xh. Then if it's this side over here, I've got x times h, which is xh. So my total surface area is this 2x squared plus 2 of each of these. So I've got my 2x squared plus 2xh times 2 plus 2 times the xh there. So 2 times this and 2 times this. And I know that that equals 24. So what I can now do is jig this about and do something to get rid of the h itself. So what I can do is if I shift the 2x squared across there, I get 4xh plus 2xh equals 24, take away 2x squared. Here, if I look, I could take out a common factor of h. So I then get h bracket, well, 4x plus 2x gives me 6x. So it's h times the 6x equals 24, take away 2x squared. So now what I want to do is rearrange this to make h the subject of the formula so I can get rid of the h there in the original equation. Divide both sides by 6x, and I get h equals 1 over 6x, bracket 24, take away the 2x squared. Now, if you notice the bracket here has 12 minus x squared, so what I'm able to do is take a common factor of 2 out here, and simplify, and I'll end up with 1 over 3x, bracket 12 minus x squared. 2 out, 2 over 6x, 2 and the 6 cancel to give me 1 over 3x. What I can now do is take this and substitute it back into here. So what I can then say is my v of x, my volume, equals 2x squared times this. So it's times 1 over 3x, bracket 12 minus x squared. And I can simplify this to get 2 over 3x, bracket 12 minus x squared. There you go, I've proven the formula, I've shown the volume is equal to that. My next step is to do this part here, so find the value for x which gives the maximum volume. What is the volume? So to get the maximum, as soon as you see something like that, you're thinking it's optimization, so I need the derivative. Now to do that, first thing I'm going to do is multiply at the bracket. What I get there is I get 24 over 3x. Well, 24 divided by 3 gives you 8. So I get 8x, take away 2/3 x cubed. We then take the derivative of this and set it equal to 0. So I get v dashed of x equals 8. Take away, we'll bring the power down. I get 2 times 3 over 3, so 6 over 3, which gives me 2. So I get 2x squared, and that equals 0. So I can solve this, shift the 2x squared over there and then divide by 2. So I get x squared equals 4. So x equals plus or minus 2. Take the square root and you get two values, plus or minus. But if I look at the scenario, I want a base with a length of x. If I choose x to be negative 2, I'm going to get a negative length. So I can discard that solution from my calculation. And I can then simply say, therefore, x equals 2. What I can then do is take this and show it gives me the maximum. So to do that, that's where our nature table comes into play. So our nature table comes into play there. I've got 2 just above, and 2 just below. Now, one key thing I'm going to highlight, when you're doing a nature table like this, and it's a scenario, your derivative here, don't just write d by dx. Put it in the context of the question. So my derivative here is given by v dashed of x. So that's given by v dashed x there. We then have the graph as well underneath. That bit doesn't change. Put this in though. This will cost you marks if you don't put it in the right context for the question. Now at 2, we know the derivative is going to be 0, so it's flat. Let's say just below 2, so approaching it from underneath, let's say it's 1. So that then gives me 8 take away 2 times 1 squared, 8 minus 2, 6. So it's a positive value, it's coming up the way. If I then look at 2 just above it, so let's say it's 3, I then get 8 take away 2 times 3 squared, 2 times 3 squared is 2 times 9, which is 18. 8 minus 18 gives you a negative value, so it's going down. Therefore, x equals 2 is the maximum. X equals 2 gives me my maximum value. What I can then do is calculate the volume from that. So I substitute that value into here, and I get my volume. So I'm then after v of 2, which I know equals 2 over 3 times 2, bracket 12 minus 2 squared. So 2 over 3 times 2, that gives me 4/3 times, well, 2 squared is 4, 12 minus 4 gives you 8. So it's 4/3 times 8. What that then ends up giving you is 32 over 3. So it's 32 over 3. Put it back in the context of the units, cubic centimetres. That there's my volume, the maximum volume the cuboid can give you, which is given when x is equal to 2. This is your classic optimization style question. You have to bear in mind all the key properties here. So showing the volume, you've got two bits of information there you can use to do it. Yes, you've got a variable here, h you don't know, but this surface area part here gives you some information you can use to eliminate it. Then you can plug it all together and show the formula it's after. Second thing, it's asking you for a maximum, so whether it's a maximum or a minimum, it's the same set of steps and the same idea. Calculate your derivative, set it equal to 0 and solve it, and then show it's a maximum or a minimum. Remember, look at the context. I couldn't pick the negative here because I can't have a negative length. That logic holds for everything else. And when you're doing this stationary point table, and you're looking at your table of values, remember this. Put it in the context of the question. It's v dashed of x, it's not d by dx, unless that's the context, unless it's an equation given by y of x equals. Put it back here, don't cost yourself a silly mark at that point.